Hello everyone. This video I'm going to demonstrate an example for simple harmonic oscillation, and it's your homework problem. Not this one. It's a homework problem. I forgot this number. It's homework problem 13.67, and this problem I think it probably how to say, I think it probably is over your capability too much. Okay, so but I still making a video for you. Okay, I think the math in this problem is way beyond your capability right now. Okay, okay, so here's problem is, okay, so let's say initially we have a spring and its elastic constant or force constant is what's the value? Okay, 74 Newton per meter. And then it what's called, it mount a mass, a block. Okay, its mass is 550 grams. It at beginning is a spring a spring at the relaxed. Okay, and it mount the mass, a block on the spring, and then you will imagine like among the spring, and then you will start to do the oscillation, right? Okay, and this is its initial position x equal to 0, and at this point its velocity when you mount the spring, you mount the block on the spring, and at the very beginning you hold the block and doesn't want the block to do any motion, right? So its initial. Okay, so it's also give you the initial condition at t equals 0. Okay, x equal to 0, at t equals 0, x equal to 0, and v also equal to 0. That's the initial condition. And then he want to, and then this problem asks you to find out, okay, the period. Okay, let me see what the problem say. Let's go back to the problem. Oh, no, not this one. What's the problem? That's 60.7. Yeah. Find the amplitude and period. Okay. Find amplitude and period. Okay. The problem asks you find the amplitude A. Okay. And period. And period, in this class, I call it T. Find amplitude and period based on this information. Okay, so I think I just mentioned, okay, it's still doing a simple harmonic oscillation, and I define accordingly. Maybe I just do a little modification here. Maybe it's different from my notes, but I think the answer is the same. Okay, I call it this is equilibrium position, and everything below means x greater 0, and everything up means the less than 0. Okay, so after I release the spring, it started doing a harmonic oscillation motion around the equilibrium position. Right now I don't know the equilibrium position, but I don't have to really know that. But I don't have to really know where is the equilibrium position. Okay, and these two graphs, I just want to show you. Okay, this is also the oscillation because the spring force. Okay, when it goes down, the spring force trying to pull it up, and this is spring. And when the block goes up above the x equals 0, the spring just want to push it back. Okay, so it's pulling down. It's with spring. So, okay, it's the same with we see simple harmonic oscillation. Okay, or in all the feature of oscillation, your force is always opposite to your moving direction. And now if he's going down, but the spring try to pull it up, and it goes to up, but the spring trying to pull it down. Okay, so your moving direction and force are always opposite. That's the feature of oscillation. So actually, any spring force and sigma F equal to ma. Okay, and F right now, if with spring force is always opposite to your moving direction, right? So and then it will has a minus sign. Okay, minus kx equal to m d square dt square. And okay, but this is not the complete equation of motion of this problem, because in this problem, because it's vertical spring. Okay, in previous in the lecture, we are assumed the mass spring system doing motion in the horizontal direction. Okay, but right now it's moving in vertical direction, moving in vertical direction. So there will be an extra force. What's an extra force? I think you know that. Okay, that's extra force. Okay, extra force. Okay, mg point down, mg point down. Okay, mg point down. So we have another force, and now I say everything below x equal to 0, everything point down is positive. Okay, so it's mg. Okay, we have mg here. Mg is keep mg is act as a constant force in the a constant force apply on this simple harmonic oscillation system. Okay, so this is equation of motion. Okay, this is our equation of motion. Okay, equation of motion of this system. Okay. Okay, from the equation of motion, if we can solve the equation of motion, we can solve everything about this motion. Okay, and that's the beauty of equation of motion. Once you write down the equation of motion, can give you initial condition, you can know almost know everything about the system. Okay, so let's do a little arrangement for this equation of motion. So, okay, I say it's m d square x dt square, and okay, plus kx equal to mg, and we divided this equation by m mass. Okay, plus mk over mx equal to g. Okay, that's over the second order ordinary differential equation. Okay, and the first problem is okay, not the first problem. The problem want to ask us to find out amplitude and period. Okay, let us answer the period very quickly, because period easy to use, easy to answer. This term it's the same as in the simple harmonic oscillation. Okay, in the simple harmonic oscillation, it's 0 here. Okay, but right now we have extra g here. Okay, that means this system is subject to external force, okay, or external acceleration, and external acceleration is a constant g. Okay, the system has experienced an external acceleration. In the simple harmonic oscillation, moving on horizontal direction, there is no extra acceleration. Okay, and also in the vertical mass spring system, this is also we call it omega square. It's also angular frequency. Okay, so omega square equal to k over m. So that's angular frequency is equal to square root of k over m. And what he want to us calculate the period. And I know previously I showed there's a very useful equation to convert the period and angular frequency, and omega t equals to 2 pi. So t is omega 2 pi over omega. Okay, omega t 2 pi. Okay, so what is our period? Our period will be, that's the reciprocal of omega, so it's equal to m over k. So we can calculate the value. Okay, because mass is there. Okay, mass is there. Okay, maybe I calculate here. Okay, because the mass, okay, t is equal to 2 pi. Mass is already give us 0.55 kilogram. Yeah, transfer to MKS system. And force constant, elastic constant is 7.5. Is this right? 0.55 divided by 74, and take the square root and times 2 times 3.14. 0.54 is a period, correct? Let me check. Yeah, I think the answer is right. Okay, let me check. Do I write anything wrong here? 0.54. My answer is 0.54. Okay, 0.54. Okay, then the unit is second. Let me check. Do I write something wrong here? K over n omega. So omega t equal to 2 pi. So t is 2 pi over omega. So, okay, I think it's right. Okay, 0.54. Second, that's period. Okay, so it's easy to answer. And the next problem is we have to find out the amplitude. Okay, how to find this amplitude? And previously, we demonstrated example in the lecture, say if we can use equation of motion, and if we have a solution of equation of motion and put an initial condition, we can find amplitude and phase constant, right? Remember that? Okay. Okay, so right now we have to solve this differential equation. Okay. So yeah, I think that's why at the beginning I said this problem may be over your math skill right now. So okay, so this problem may be over your capability right now. Okay, so actually also we still have to solve the, we can also solve this ODE, and this the solution of this second order ordinary differential equation has two parts. One is homogeneous solution, the other is particular solution. And xh is the solution of this differential equation, the same differential equation, but without the external acceleration. Okay, that's called homogeneous solution. Okay, and so this homogeneous solution is back to the simple harmonic oscillation equation. So let's tell you your homogeneous solution is just your solution of simple harmonic oscillator plus phi. Okay, oh, there's no problem. Okay, but I know this is beyond your capability right now, but I still have to solve this equation for you. Okay, maybe after all, if after you're learning engineering mathematics, you understand what I'm talking about. Okay, and next is solving the particular solution XP, and for solving the particular solution, okay, because it depends on your extra your fourth term here. Okay, it depends on your term in the right hand side of the equation. The right hand side is G is a constant. G is a constant. So when you're trying to solve in the particular solution of second order ordinary differential equation, and your fourth term is you see this particular solution depends on your fourth term. Okay, if your fourth term or external fourth term is a constant, so you just assume your particular solution is just also a constant. Okay, let's call it constant, call it C. Okay, let's call it constant C. Okay, if this right hand side term is one power one function, you just assume it's power one function. It's power two function, just assume XP is power two polynomial. It's power three function, it just assume it's power three polynomial. Okay, but let's engineering mathematics. I think right now you don't understand. Okay, so let's assume the particular solution is a constant. So let's assume the solution, and what the meaning of solution? Solution is valid for the original equation. So you put this C back into your equation. So you will see this C dt squared plus omega squared C equal to G. Okay, because we assume a particular solution is just a constant, so this term is going to 0. Okay, so we can find our G, our C. It's very easy. It's just the G over omega square. Okay, so finally we get a solution is XH plus XP. XP is the solution of simple harmonic oscillation. And when we plus the particular solution P is G over omega square. Okay, and so if we get this solution, okay, what's our initial condition? Yeah, at the very beginning, I tell you, okay, at the very beginning, when we mount this block on the spring, And we just assume, okay, let mount position x equal to 0, and velocity is also 0. Okay, velocity is also 0. Okay, so your initial condition is your initial condition is when t equal to 0, x equal to 0, and at t equal to 0, velocity also equal to 0. Yeah, we also have to get the velocity function, but it's very easy to get a velocity function. dx dt is just our velocity function. Okay, dx dt, doing the derivative with respect to x with respect to time. And it's very also the same when we do the simple harmonic oscillation motion. This will become minus omega a and sine omega t plus phi. And because g is constant, omega squared is all constant, so after derivative it becomes 0. Okay, so we have the position function, okay, and the velocity function. Okay, so let's see. Okay, let's put the initial condition in at t equal to 0, x equal to 0. Okay, so if t equals 0, plug in. So we have a times cosine phi plus omega squared and g. And at the initial position, well, velocity is also 0. Okay, well, velocity is also 0. And our velocity function is minus omega a, and sine times sine, and this should be phi. Okay. Okay, that's our initial condition. So I think we can solve this solution now. Okay, we solve for velocity function first. This looks much easier. Okay, omega times a times sine phi equal to 0, because but omega never be 0, amplitude never be 0. Okay, because doing simple harmonic oscillation, there must be some amplitude. So we will get the sine phi equal to 0. Okay, what's the simplest solution for phi? If sine phi is 0, what's the simplest solution? The simplest solution is phi is equal to 0. Okay, so we put a phi equal to 0 back to the equation 1. What we have, so 0 is equal to a times dot the cosine 0 plus omega squared g. So it becomes 1. So okay, we can solve this out. So amplitude, it's negative sign. This is it's a kind of little strange. Hmm, it's kind of little strange. A is because A become a negative value. Hmm. So is there if the sine equal to 0, find pi sine pi cosine pi? Hmm. Okay, let's start. Let's continue. A equal to minus g over omega 2. Okay, so that's really pretty very strange. So we have the we have amplitude is a negative value. Oh yeah. And because in this system, I assume everything point down is positive, point down is positive, point up is point up is negative. Yeah, that's very strange. Okay, never mind. Okay, so yeah, I have a sign issue here where we can just temper and ignore this. Okay, what is so this amplitude? What is the we just temper ignore the minus sign. Okay, so our A, if just put the g of omega square, what's the value? G is equal to g times omega square, 1 over omega square. Omega is square, omega square is k over m. So omega 1 over omega square is km. So it's actually mg over k. Okay, m is mass. What's the mass? 0.55, remember, times 9.8. And the k is, what is k? What is k? K is, so 774. Okay, over 74. Okay, so 0.55 times 9.84. So I think it's 0.0728. So it will become 7.28. This is meter, okay, and it will become centimeter, about 7.3 centimeter. Okay, and after solving this problem, yeah, we have a problem with a plus negative sign, plus and minus negative sign. It's very strange. Yeah, I think it's because of coordinate system. Okay, but the magnitude is the same, but it's just plus or minus. Yeah, I think for this short time I cannot figure that out. I think it's because of the coordinate system, or the I missing something. Yeah, yeah. In my notes, I assume a point everything point down is negative, point up is positive, and now I define a point down is positive, point up is negative. It's kind of reverse, but initially I don't think there would be a difference. But after all, yeah, still have the amplitude still have some issue here. Yeah, it's negative, but the magnitude is right. Okay, the answer is 7.28 centimeter. Okay, but anyway, this problem is right now beyond your capabilities. So I just still do some demonstration for this problem. But there won't be a problem solving a differential equation like this in your final exam. Okay. Okay, so I just start video here. Let's see you next video. Bye bye.